Matter and electric force. Our material world is made up of these tiny, wonderful things called atoms. Atoms, in turn, are made up of tiny particles called protons and neutrons, which are in the nucleus, and these buzzing things around here called electrons. The strong nuclear force is what holds the protons and neutrons together inside of the nucleus. And it is a very strong force, about 100 times stronger than the electric force. But the strong force does not reach outside of the nucleus. The strong force is only contained within the nucleus. So the world outside of the nucleus of atoms is governed by the electric force. And it is the electric force that holds the electrons buzzing around in their orbitals outside of the nucleus. There are only two ways that protons and neutrons can be smashed together close enough for the strong force to take hold. One is in the very center of stars, and the other is when stars explode and protons and neutrons can slam into one another. Smaller atoms can slam into one another and make bigger atoms. So literally our entire material world has been manufactured by this in the center of stars and by the explosion of stars. Our wonderful universe was around for 9.2 billion years before some stars exploded in the outer ring of the Milky Way galaxy and created a nebular dust cloud. And from that nebular dust cloud, all of these elements, all of these atoms came together and created a wonderful planet that we call Earth. There are 90 of these atoms that are found naturally on Earth, and we can kind of think of them as Legos. Legos are different shapes and sizes, and they have different types of clicks, if you will, that give them a certain strength of connection when they connect to other Legos. Let's start by talking about the different shapes of atoms. Atoms aren't simply spheres. They have rather irregular shapes depending on what are known as orbitals. And these orbitals are governed by the laws of quantum physics. And so atoms are built kind of one layer at a time, one orbital at a time from the inside out. And as the layer of orbitals increases around an atom, the geometry of the shape of the atom can look quite unique and rather beautiful. So again, atoms have different shapes that are governed by quantum physics. So it's Coulomb's law that holds these electrons buzzing around these protons because they're electrically attracted to them, but they buzz around in these quantum orbitals. Now, this is quite a complex interaction because it's not just a single pull here. This electron is being pushed by this one and pulled by, and also pushed by this one and pulled by these protons in here. And so it gets quite complex to calculate all of this. And they also don't buzz around in nice, even spheres. They go around in these quantum orbitals. So instead of looking at all that complexity, we boil things down to an idea of a charge density. So atoms, depending on their electrical makeup and also their quantum configuration, display kind of a particular overall charge, and that's the charge density of a particular atom. Some might be positive, and some of the atoms might display negative charge densities, and it's the overall charge density between individual atoms that tugs the different atoms together and clicks different atoms together, just like Legos click together. In chemistry, this complex interaction between Coulomb's law and orbitals boils down to one quantity pretty much that they call electronegativity when you get into chemistry. And so what electronegativity does is it gives a relative amount of the connectivity, if you will, between atoms. You can see over here that we have some very reactive atoms with nitrogen, oxygen, fluorine, chlorine, bromine, And they're very reactive, and some of these are quite reactive as well. As you go down here to cesium, not so much reactive. And then there's the unique hydrogen atom that has unique properties. It's also quite reactive. So electronegativity, when you get to chemistry, is the way chemists talk about the interaction between Coulomb's law and these crazy quantum orbitals. Electronegativity also doesn't just talk about how reactive elements are, how much they're attracted to each other, but it also gives a descriptor of how they click together, or if they click together. If you'll notice here, the noble gases, these are inert, meaning that they don't interact because they don't have any dots, if you will. They don't have any pull toward one another because they're complete with their shells, and they don't have any electric charge density around them. So these don't react. Now these other ones, in addition to the reactivity, based on electronegativity, you can tell how they click together. Legos click together with just these dots, but we're going to see that in our Lego world of atoms, there are 3 ways to click atoms together, not just the single Lego type way of clicking them together. So the 3 types of clicks, if you will, clicking atoms together. We don't call them clicks, though. In the world of chemistry, we call them bonds. So there are 3 types of bonds in chemistry. There's ionic bonding. A common one here that you'll recognize is regular table salt, sodium chloride, NaCl. And that's the most like a regular Lego click, and we'll see that. Then there's covalent bonding, and the most familiar one probably to all of us is the water molecule, H2O. This is not like Legos. And then there's metallic bonding, and this is a very unique way that metals bond together, and this is a common look at copper. And again, this is not very Lego-like. But anyway, these are the 3 types of clicks together for atoms that make up our wonderful world. Let's start with a look at ionic bonding. Here's our ionic bond right over here. As I said, this was most like Lego clicks, and that's because ionic bonds are between these purple elements called metals and these green elements over here, and also hydrogen, called nonmetals. And a metal is an atom that is close to having its quantum structures perfectly balanced and nice and pretty, but it's imbalanced by usually 1 or 2 or 3 excess electrons. So if it can get rid of electrons, then it can have a nice, pretty outside, complete quantum structure. On the other hand, these green atoms here, these are nonmetals, and they're really, really close to having a perfect quantum balanced structure, but they need electrons. So they'll readily take electrons from these metals. So the metals and nonmetals get together, and the metals give up an electron to the nonmetals, and they have nice quantum structure. When they do that, they're separate quantum structures, but now when they've given up the excess electron, the metal becomes positive and the nonmetal becomes negative, and they're called ions. Now there's a big electric force between them, and they hold together really strongly with the Coulomb electric force. And it's that strong electric force that really gives it its characteristics, kind of like the click of a Lego. Next, let's talk about covalent bonds. The first thing you probably notice here is that covalent bonds come in 2 flavors, polar and nonpolar. And I'll get to that idea in just a second. But first of all, a covalent bond is where these nonmetals, these green atoms here, and remember that the nonmetals need an extra electron or 2 or 3 to fill out their quantum orbitals to have a nice stable structure. And so what they do is that instead of giving up electrons, they actually share electrons. Now when they come together to share their electrons, it's really kind of cool. they don't have individual quantum structures. When they get together like this, their outermost quantum structures actually configure and meld together into new hybrid quantum orbitals, which are quite cool. When they do come together, if they come together of the same type of atom here to share, their structure ends up being very uniform and symmetric. Notice that it's symmetric about this axis and quietly asymmetric about this one. So there would be a little bit of electrical density variation here, but very little. So these don't form other bonds as well with other molecules. So this molecule is a nonpolar molecule. When you get a polar molecule, notice that there is an asymmetric electrical distribution now. What happens is in their quantum structure that they form together is the electron will spend more time on one side of the molecule than it will on the other. So that'll end up giving the molecule a little bit of an electrical polarization. That's why they're called polar covalent bonds. Now these are kind of cool because these molecules then can click to other molecules and form other covalent bonds. And that's we're going to see is super important for our world. So these are nonpolar and polar covalent bonds, and these are ionic and covalent bonds, two of the three kinds of bonds or cliques, if you will, holding our atoms together to form molecules. The last kind of a bond is called a metallic bond, and the metals over here, remember, needed to give up electrons to have their quantum structure be well defined. So if these metals come together and this metal had to give up 2 electrons to become nice and stable structurally, when they give up those electrons, they don't share them like in a covalent bond, and they don't give them up to the other metal who doesn't want them anyway. So what they do is they just kind of all throw out their excess electrons that they don't need, and those excess electrons become kind of like a sea of electrons, a fluid, and that forms an electromagnetic kind of a glue, but it's a flexible glue, so it's very unique. So what ends up happening is there ends up being very strong materials here and that's why metals are very strong, because they are pushing away from each other electrically with their ions, but they're also being attracted to this interstitial fluid of electrons that are holding together. So it's a very unique electromagnetic glue, if you will, and both a study of repulsion here and also attraction that really lock them in to make really strong materials. Another unique thing is that these electrons really are free to move about. They're not bound through like covalent bonds with the quantum orbitals, and they're also not bound to the atoms like they were in ionic bonds, and so these electrons can move about. Now they have to have an equal distribution on average. We can't have a whole bunch of electrons leave here and leave these without electrons. That doesn't happen because of the strong but any one electron can kind of float as long as another electron floats in. So that's why they become pretty good or very good conductors of electricity. These are metallic bonds. So again, it's these 3 types of bonds, ionic bonds, covalent bonds, and metallic bonds, that click our atomic world together. There is one last form of bonding, and that's molecule-to-molecule bonding, like you get with water here. And that's why water has its properties as it does, that it can move about easily, because these are pretty weak intermolecular bonds. But you can have some fairly strong intermolecular bonds here where the molecules are very closely packed together in regular formation with long strips, and you can form materials like Kevlar. So intermolecular bonding is one last way that Coulomb's law holds all matter together. So in the end, it is the electric force and also quantum orbitals that govern all the behavior of our Legos to create our wonderful Lego land. So Scratch's parting thought, and good luck on your quest for continuous improvement.